The last class on models will be today. We'll add two more new models that we haven't talked about yet so far. First, a hint for stipends, grants that you can apply to support your studies. There are two deadlines approaching, one for Rory Auerbach and Minerva, which are offered by our university. So there are real grants that are available. Somebody gets them, so if you want to be among those the selection is being made, you can apply. If you not get selected, there are plenty of other stipends and grants that you can always try to get. There are more than one expects, and you don't always have to have excellent grades. Good grades are sometimes sufficient to get something. So, a good opportunity to finance your studies. A brief remark on the homework. I think that was pretty straightforward. There were very few errors there in the Ngram homework. One thing, there is a difference. Did we correct that already? No. Did we give some answer? One difference in the solutions, you can come up with different numbers, but this can be correct, is what do I start with? Is blank part of the Ngram or not? That's something has to be defined, and you can work with either one. But of course, there is no trigram or something or a bigram that has only one character. That's undefined. Two blanks or something like that doesn't exist. And also, there is no definition for a similarity among three objects. There's only pairwise. It can only be pairwise similarity, something that we also dealt with frequently. Okay, other questions on the Ngram homework? I think you should have gotten. No, that was on paper, right? I have to hand back the paper to you. But there will be, I think there should be frequently a file where you can see how many homeworks you've already successfully. Is it already online? Okay, also okay. So my supporter, Mrs. Furtner, also put that online, and then you can check. Great. There will be more homework today. Weight normalization is now being worked on, right? Number 4, I think. There will be one today on language models. Oh, it's still misspelled. Anyway, probably one on evaluation, and the 7th one will be probably on an experimental learning system where you can work with algorithms and try out different combinations of variations of algorithms. That will be out then, probably the last homework. Questions? No? The second exam I mentioned it. I put it in the on the LearnWeb, on the discussion forum. I checked the schedule, and there is no time really to do a repetition exam a week afterwards. It doesn't work, and then we have to wait for a longer time. And since the course takes place again in the winter term, people can take the exam there. If you're gone for the winter term, abroad or something, then you have to wait for the next summer, when there is a repetition exam for the winter guys, so to say. Okay? Question on that or resolved? Okay, good. Okay. So, questions? Looks strange? It's too pressed, isn't it? Yeah. I don't know how to change it. I'll have to ask the guy who works with this. Looks strange, looks different here, but since 2 weeks now it's like that on the beamer. Anyway, but it's readable, I hope, and today I think you will be able to see most things. Maybe it looks worse for websites in the morning, but for IR should be okay. We talked about the different models. We started with exact match, which is Boolean search, the old style, which we have still in the library and in special domain information systems. We have an extension, extended Booleans. We talked about fuzzy theory, fuzzy set theory. to also get an idea about fuzzy sets. Then we talked a lot about vector space model, where we had vectors in n-dimensional space, where n is equal to the number of terms in the collection, and there we had different similarity models. Same direction of interest, we could say, is an angle-oriented, like the cosine angle-oriented definition, or we can think about distance-oriented metrics like Euclidean distance, things like that, or block distance, things like that. There's also the probabilistic model, of course, where this is interpreted as the probability of relevance for under the condition of a certain query, but that doesn't change really a lot in the calculation. And today we'll briefly touch the language model, which also doesn't bring in completely new things, but it's an interesting new aspect. Some new things will be there. And we'll talk in the end about one of the network models that is quite different in the idea from the metaphorical approach. What is search really, but also easy to understand. Anyway, statistical language model, we talked a lot about already, about distribution of the frequency of words in a language, Zipf distribution, remember last session. And of course this is important. If we count words, we have to know how often does this word occur in average. How often should we expect this word, right? If we use the number in one document as an effect on the ranking system, then we should really consider that. And the language model takes that one step further. It says, let's take a probabilistic model, a probability model of a language. What is the probability of a certain sequence? Like today is Tuesday, can have some probability, or the sequence of words typically, but in reality we work typically with single words, not sequences, and again we assume independence, which is of course not always true. And the language model basically says, the assumption of independence, it says basically what is the probability of the generation of a document given a certain query. A certain query is taken as a probability of a language model over certain words, like a Zipf distribution, but just for a query or just for a document. And what is the probability that this query language model leads to the document language model? So distribution of probabilities over single words, estimated based on the frequency of a text, and of course weighting as probability for the occurrence. Again, we start off with our observation that language is words are distributed according to the Zipf distribution that we had a closer look at last time. And this can basically be seen as a step function. We have a number one most frequent word, second frequent word, and so forth. The steps are not as steep as they should be, of course, but for illustration. And we can have a simple probability, the frequency of a word divided with the number of all words. That's the probability that this word occurs somewhere. Okay? Nothing new so far. Everybody can still follow. So the language model in IR says this is a new metaphor now for search. Search is like, well, if there is a language model of a given query, what is the how probable is that this query model leads to a document model? Every document would have an individual distribution of frequency. Basically, this is a language model. It's simply the frequency of the words in a collection or in one document, ordered by their rank, and we had their frequencies here. Basically, frequencies transferred into probabilities by dividing them through the number of all the words in one document or in one collection. So we can have a different language model, of course, for one document that talks about whatever, wolves. Let's say with this example, we would have the word wolf at a higher position than on average. that would make this document special, would have a language distribution that is different from an average language model, would have a language model that is different from another language model of another document or of the overall collection. And that would make it interesting, special for a query that has to do with wolves, obviously. More likely that this leads to the document. Sounds all very familiar. Now, one thing that is really new is the so-called smoothing of the distribution. What does that look like? Language model wants to transform our strange step function that is mathematically a bit difficult to model. We have learned already that how we can model this in the ZIP world. Last time I also put the spreadsheet online with these simple examples. And the language model wants to make, again, a smooth function out of this step probability. Of course, the overall probability cannot increase. And, interestingly, it wants to assign a certain non-zero probability to all the words that do not occur in a special document. So, I have a even. That means, in practice, even if I search for a word, if my query word is not in the document, I still have a low probability of finding this document. Cases where none of the words is in there or something like that. So, we take away a little bit of the probability of the occurring words, of the high-frequency words, and give that to the zero words so that they have some probability different from zero, very small though, of course, and we move the function also. For example, very simple way to do that is to find a curve that runs through all points, to all data points that we have measured in our ZIP distribution, that we have observed, and we can have the add one method that says if the word doesn't appear, I assume it appears once. So I don't take the probability of a word in document is not really the count, CV in D, which is in front of the red plus 1 here. That would be the normal word count simply. It is divided through the vocabulary size, actually to the length of the document in general. Well, that gives me the probability. I move from the word. Word wolf appears 5 times. That's an indicator of whatever, relevance and so forth, of the aboutness. Now I say, it appears 5 times within 100 words, so the probability of the occurrence that any word is the word wolf is 5 divided through 100. Also very straightforward. So that would be C, the wolf count in the document divided with the words, with document size. Word count in the document of word W count divided with the number of the length of the document, size of the document. Now we have those that have 0, and we say, okay, we want to assign something to them. Let's give them a minimum number. The minimum number is 1, a natural number. We say plus 1 to all the documents. That means I assume that all the words appear 1 time more often than they really appear. That gives me V, vocabulary size, more probability basically. Right? So in order that the overall probability stays 100%, we also have to include V, the vocabulary size, in the division to make up for this plus 1 that we add here for every word. For every word we also give a very small probability. So we see if this is 0, we have 1 divided by the document size, 100, 1,000, whatever number of words there is, and divided through the vocabulary size, which can be 10,000, 30,000 or something like that, typical vocabulary size. We end up with a quite small number. That is a really small portion of probability that we give to the non-occurring words. For example, in a very small toy example again, 3 documents, 3 3 terms. We could calculate, we have the counts here, the word counts. Now you could calculate weights according to whatever formula we have learned so far. IDF, TF, and so forth, right? We know that. Now how does the language model calculate the weight? We smooth, and we give, and the smoothing leads to a situation where we don't have zero values, right? Even in TF, IDF, we would end up with zero values for words that don't occur in the document. And here, we would have a vocabulary size of 3. We have different document lengths, just the sum of the words that appear here. Document 3 is the longest, has 6 words. And in our formula that we had, this we add 1 and make our division. So where we had 0, like in Reform for document 1, appears 0 times, we add 1. That makes it 1 divided by 4. Plus 4 is D plus V, document length, which is 1, plus vocabulary size is 3, makes it 1 out of 4. Or, example, Reform for document 3, we have a count of 5 words. 501 is the vector for document 1, for document 3. Okay, all are smoothed, and we end up with 6, 5 plus 1, divided by 9. 9, document length plus vocabulary size. 3 plus 6 makes it 9. 6 divided with 9, and 1 divided with 9 for B, which didn't occur for part A. So we end up with probabilities, all add up to 1 for each document. And these are now the language models that are a bit smaller than our ZIP distribution. Right? We only have 3 steps now, but they follow a smooth function, and that's a straightforward way to calculate the language model. And a way to do weighting, to calculate weights, that we can use now again in any matching function like the vector space model, like any similarity function. Okay, questions so far? Understood? Straightforward, right? Nothing really difficult. Maybe easier than IDF even, right? So, anyway. Now there's a big problem, of course. The add one, now we come to something that is more similar to the IDF. So far we treat all words equally. So a very frequent word gets the same smoothing, the same addition of 1 than a rare word. And there the theory had a better idea. They said, okay, let's consider the general frequency of a word in a general collection, like in a reference collection, my collection, or in a reference collection for all the biggest German collection or something like that. And we calculate the probability of occurrence of a word in that general large reference corpus that is representative for the language that we're talking about. So P, probability of a word that occurring in reference collection. That way now we can deal with the smoothing different. We have a so-called linear interpolation, which simply means we add 2 factors here. And there is a mixture parameter that controls how far the first or the second of these 2 parameters is weighted. Can be between 0 and 1, of course, right? 1 we only use this one, and 0 we only use this factor, but it's somewhere in between. And the second is easier. It's simply the probability of the word in the reference collection. And the first part of this sum is the count divided again through the document size and the vocabulary size. Vocabulary size we have to add again because of this reference, probably the reference collection, which overall of course would be 1. And that way we end up with a probability of value between 0 and 1. we had +1 here, remember, for the simple kind. We just added 1 for all the words. Now we have a mixture model where we use the real probability of that word. Is it really frequent or is it very infrequent? And that way we have a lower probability for a word that doesn't occur. It's lower if it's rare. It's high if the word doesn't appear, but at least it's a frequent word in general. That's all there is. Okay? Questions? Still straightforward, I guess. Yeah, please.
Formula, the last bit, which is P of F, ref, what does that part mean?
The reference is the reference model. Probability of the from a language model of a large reference collection. That could be like whatever, British National Corpus or something like that. For English, we say what is a real probability of a word in general usage. But can also be my collection. Like if I do a special domain-specific search for pedagogics, I will use a pedagogics reference collection from pedagogics if I do that, and so forth. So where we added only 1 for every word, we now add a certain probability that we get from a reference collection. Let's give justice to frequent words and justice to infrequent words, basically. Okay? So quite easy. It's basically very similar to the +1 method. And these are very simple smoothing methods. Of course, language model, they have come up with a lot of different things that we don't really have to know all about. So many smoothing measures have been applied, many smoothing functions. That's where research is going on. And then again, we have a new parameter that we can change for IR systems. So far we have heard lots about different methods to do IR, right? We have different different weightings. We had IDF, TF-IDF, logarithmic IDF with different bases. We had a fractional IDF and so forth. We had different matching functions, similarity based on cosine, distance or whatever in between. We have different stemming algorithms. We have different methods for stemming different rule sets. So lots of complicated parameters that make up one real IR system as it works and calculates similarities and gives hits back. And we don't know why these hits come back. It's too complicated. And only thing we can do is evaluation. That's why we, not next session, but the session afterwards, we'll talk about the importance of evaluation in IR and how this can be done and what are the problems associated with this. Language model, interesting way to think about it is the so-called divergence from randomness. This is basically what IDF is in, more or less, in the TF-IDF world. This is divergence from randomness in language model. The more the divergence of the within document term frequency from its frequency with the collection, meaning the more divergent from randomness the term is, the more information is carried by the term in the document. That means if a word is frequent in a document, but it's also frequent in the language, and the frequency is more or less the same, that word doesn't carry a lot of information for me. So far we had a definition of informativeness last time, inspired by Thomas Rölleke, that is basically based on IDF. Right? You said all frequent words that appear very often, they're not so informative, right? But a frequent term that is even more frequent, that diverges from the randomness or from the general. Randomness means basically the general corpus, the one we asked for. The more it diverges, the more it's different. Higher maybe, right? Especially higher, of course. If it's lower, it's also informative that it's not about this topic. The more information this term carries in a document. Excuse me. And this measure of informativeness, it's not a measure yet, it's just a sentence here, is also document specific. It says, yes, this term is very informativeness because it appears much more often in the document than in a general language collection. That means, basically this also means the language model, ZIP distribution that we observe for this document is different from the general language model that we observe for our language. Okay? So the distribution of probabilities of a word is different between documents. Everybody uses different words, or depending on the topic that they write about. And if the language model of my document is different from the general language and somebody's asking for it, then it's really likely to be relevant. But if somebody asks for a query term, then documents where this query term appears more or less as often as it's supposed to be, than it is expected, randomness, then that doesn't really help me so much. Okay? So that's quite interesting notion in the metaphor behind the language model. Basically, that's a theory behind to determine weights, and interesting new is also that distributions are smooth, that we assign non-zero probabilities to all words, and that is basically it. Other than that, it's not really something fundamentally new, and we see a lot of similar things that we also have seen in other models, like the TF, basically the frequency of a word, the word count. Of course, that is C of a word in D. That's basically the TF. Same thing, right? Just dealt with differently. Out of TF, we make a probability here, normalize, and we do the smoothing step. Questions? How are we doing in time? Let's see. Oh, still good in time. You can ask more questions. Is there any? None. Okay, good. Then we move to the next model. Now we have to do a little less with numbers. This is again more metaphorically. We come to artificial neural networks, and this is one of the network models that is typically used in information retrieval. Neural networks are a method that are used in machine learning or in computer science to model vagueness and learning algorithms that are capable of learning something, and these neural networks are part of also of algorithms that are so-called nature-inspired algorithms. For example, anybody heard of other examples? There are things in nature that look like more or less intelligent, and people say, "Oh, this is so great, we can use an algorithm that works similar, and this algorithm also do a lot of nice things." Somebody in computer science classes maybe. Not the case. For example, genetic programming, where the power of genetics is being used, lots of solutions are created, and only the best will survive in a genetic algorithm, and that way a large solution space can be explored quite quickly. Another example is so-called swarm intelligence, where the behavior of like bees or other animal swarms is modeled, with things that behave more or less the same, but there's some divergence in them, and that way the whole behaves quite intelligently. As far as survival is concerned, these are also examples for this. Anyway, okay, neural networks now, they model, of course, something more anyway. They model the function, the way the human or any natural brain functions on a very simple level, right? And they also very powerful. Model is, of course, natural brains. And now what do they really model? Very simple. They assume, which is of course true, that the brain is built up of very simple processes, but very many of them. So each neuron by itself cannot think, obviously, right? Only the brain as a whole can think. And neural networks say, well, let's model this. Each neuron itself can only operate in a very limited way. It can look at its input, which are very simple signals, input or non-input. Like a synapse can be active or non-active, right? There can be some activity or not. That is modeled. Then the neuron itself can look at its input, and depending if a certain sum of input if the input is over a certain limit, then it will start to send out some signals to other neurons. That's basically looked at it from a very simple level. That's it. Of course, neurons, the signals are typically don't have a strength like here. In the real brain, they work over frequencies, but that's just not such a big difference. And the way meaning is created is only by a massive interplay of many, many neurons. I can only understand the brain, it only makes sense what the brain does if I look at many neurons, right? There is no one single neuron that represents something. Only patterns of neurons' activity represent something. So we have very simple single processes. Here is a very nice statement. Put it in German because it was published in German, and it puts it quite nicely. The information processing is carried out through a large number of relatively simple processors that are connected in a dense network. These processors or units or neurons only work locally, only look at their own activity and their neighbors that they're connected to, and each by itself communicates with other units via signals and signals that are sent over connections. So, okay, we have simple things, but they're highly connected, and these simple things simple processes do very simple things. They get input and send back connectivity, sent back to other neurons. Neurons send and receive temporary activity, and now this is in our neural network model is the metaphor for the short-term memory, something that we think of right now. Our current activity in the brain, right, that we may forget in a few seconds. A few seconds later, the other cells are activated. Activation goes on, signals are sent again. Some neurons turn off their activity, others turn it on based on the pattern. And that means over different points in time, different patterns of activation occur. That is what we're currently thinking of. And that can be called our short-term memory. And something else happens in the brain. The brain can learn. And in the neural network model, this means connections change their weights, how much activity do they pass on, right? If a neuron is activated and there's a connection between neurons, it depends on the level of the connection, of the weight of the connection, of how much activity is let through. Is that everything or just a little bit? And these weights of the pattern, of the connections, they change very slowly over time. And that corresponds to our long-term memory. Things that we learn over a period of time, the weights are adapted depending on the feedback that we receive. That is basically what learning is modeled as in a neural network. Artificial neural networks that are simulated on computers that take a few aspects of our brains. So the modification of these weights is called learning, and the weights are the parameters of our system. The neurons never change. They don't do anything different than what they're supposed to. Keep calm or fire after a certain level of activity input is reached. Then they start to fire, send out signals over other synapses or connections, as we call them, and that happens. So basically, that's the all of the definition of a neural network on one slide. We have a neuron. The input of the neuron, like K, is the input of the product of the current activation of the sending neuron and this weight. And this changes over time. That's what they call the learning, the long-term model. Activity can change at any time. That's what we're thinking about right now, short-term memory. And of course, as I said, this is only one network, two neurons with one connection. We have a large network, and this happens between all the neurons involved. And we can have a simple function like the sum of the weight multiplied with the activity of this neuron can be an input for this neuron, plus inputs from other neurons, of course, right? And we sum this up, and then we say, did we reach a certain threshold or not? If yes, we also fire, we get activated synapses, connectivity out. And in most models, unlike the human brain, in the human brain we can only off activity or not. It's more or less binary. In these models we have levels of activity. Like this would be the more or less a step function as it is active as far as I understand in the human brain, activity or not, whereas in the artificial neural networks we have a logistic activation function that looks like that. I have very little input, I have very little activity, and if the activation grows, if the input grows, we go to the right. Our activation also grows. This is a steep function based that is similar to this threshold function, but of course nicer to handle mathematically. Okay? So far, understood? Or questions? The basic principle is really very simple. And of course now the way, how can I use this? How can we use such functions? We can create networks that have an input neural networks where we add some information, whatever we think about, whatever we want to model in our learning algorithm. Then we have a lot of processing steps in our huge network, and somewhere there are neurons that we have that are connected to the out world that give us the output. And anything in between is not very transparent, but if we do a lot of learning, we can tune these neural networks so that they can do very interesting things like classification of handwritten characters, things like that. This is typically what they are used for. Complex classification tasks. And they're quite successful algorithms. Okay. Next thing. How are they used now, for example, in information retrieval? And here we have the not so nice situation, but that's the way it is typically in most of our systems that use neural networks, that we don't have such a nice something is expressed by a pattern of activation. Here we have really neurons that mean something, which is not true in the brain, of course, and that's why these simple systems are also not so very successful. So each neuron, each unit stands for either a term or a document. So we have a document layer and a term layer. We could have several activation layers in between them where the neurons really don't mean anything, but for illustration purposes that's easier. So we have for each document one of the neurons, and we have neurons for all the terms. And now what happens? We have the connection to the outside world. That means the user, how does retrieval start? The user is interested in something. So he activates a query word. And that means this neuron representing this query word will start to send signals out to the network. Now what is the connectivity matrix? Another not so nice thing about these kind of neural networks. As we've said, the real knowledge, the long-term knowledge is in the connections. And in this case, we have initiated these connections with our weightings, with our weights. So if I have no connection between LAN and document 5, that means the weight is 0. In our IR world, that means LAN does not appear in this document. So there is no connection between them. Right? If there is a high weight, like network for document 7, then we have a strong connection. Implicitly shown by a stronger line. So we see each connection is one of our cells in our document term matrix, in our weight matrix, and is initiated with the weight value. So this is a connection that leads through lots of activity, whereas this doesn't leave through so much activity because it's weak. It's a weak connection between LAN and document 6 because it appears not so often in document 6, right? The word LAN. Okay? So the real knowledge is in the connection. This can change over time, of course. So learning algorithms like Hebb's rule means, Hebb's rule, for example, is one that says connections where activity flows very often are strengthened. Others decay over time. But so far we assume that this just represents the knowledge that we have in our documentary matrix. Now, as I said, the user initiates retrieval. He says, I'm interested in TCP, types TCP, and this gets activated. And now it sends signals to document 6 and document 7, and these will also get activated. And now, so far it doesn't look very exciting, right? I type in TCP and I get 2 documents that contain TCP. Not such a big deal, but the network has some nice features. Any ideas? What could happen now? Hmm? Sure, also questions. Anyway.
The circles, they are bigger and slower. What is there any special meaning, or just to show it's activated or not?
Yeah. This the strength of this line just means activation. They should all be of the same size. Size doesn't matter. Maybe it's squeezed or I didn't draw it nicely, but basically size should be the same, and the activation level should be illustrated by
so
answered?
If TCP/IP is activated, document 5 is activated, and also everyone is connected with document 5.
Yes, and that's an interesting issue.
So then network and document 1. But document 1 is not shown as activated.
Okay, yeah, that's because I didn't draw all the conclusions also very nicely, yes, right? Okay. And now, but that's a very interesting thing that you just mentioned. In typical retrieval scenario, we input TCP/IP, and we get 2 documents that contain TCP/IP. Over, process is over, okay? And here, these connections can be passed on in both directions. That means this layer activates the document layer, 5 and 7 at first, and then the document layer activates again the term layer. And now we get documents, new terms that were not in the query, but they are somehow related to this because they appear in the same document. Document 5 also has network. And our network starts to be activated, maybe not as strong, because it's not a strong connection, maybe it's too cold, and it activates a lot of other terms that documents that are associated with it, that appear in the same documents, right? With a strength depending on the weight. So this process can go back and forth several times. Of course, we need the factors to decay also, things that are activated but then are not really so interesting, but don't get activated strong. Only things that get activated several times by several processes, they seem to be interesting. So here our metaphor for retrieval can be, I ingest some interest of mine, I express my interest by activating some query, and my interest spreads over the network, and all things that I'm interested in get activated. Topics, terms or document, doesn't matter. I can also use this to get interesting terms back. Of course, it could happen that terms get activated that I'm not interested in. Of course, this also has negative effects, obviously. But it's a spreading, and they are called spreading activation, as we see there. The spreading of the activation can be seen as a spreading of my interest in a closely connected network of units representing some knowledge, being documents or queries, documents or terms. So I add TCP/IP, and other things get activated. They are associated with it. Later we'll talk about this. We'll learn this method. We will also talk about this method in other concepts and its relevance feedbacks. I think we did it in the pattern class also today. But here, we don't have to invent something like relevance feedback. It's just natural in the network. I can activate somewhere, and my interest will spread, and things that I'm interested in will get activated. Other ideas, other things that can be handled very flexible here. In a typical IR system, I have to add my interest by query, right? Quite obvious. Here, I can add my interest anywhere. That means I can also say, hey, I'm interested in document 7, I just read it, I'm interested in it, this is my input. I won't have to change anything about the algorithm. I add a document as a query. Find similar documents, find terms, and then go back and forth, and then I look at the very highly activated documents, and those are my results. Okay? Questions or remarks? So I have a quite powerful model. The metaphor is my interest is spreading through this network of objects, of elements, and it's quite flexible. I can have a document or a term as an input or both. I can add a document and a term and wait what happens. Yes, please.
I'm sorry, but I didn't really get what the learning process in this model means.
Yeah, what does learning mean here? That's a weakness of the spreading activation models. They typically don't include learning. Learning means the long-term model is injected before. Just my term, my document term matrix is injected into the connectivity matrix, into the strengths of the connections. Period, so far, for the spreading activation networks, right? However, neural networks, they include different forms of learning processes. One is, for example, Hebb's rule says synapses between neurons that we use a lot, they are strengthened. They get a higher weight. And that's something we observe also in natural brains, right? Learning is one way learning happens, is that synapses that we use very much will be more, basically a high weight, that activity flows better between them, even by growing closer together, right? Or by expelling more yeah, what are they called? There is one process when the electric transmission changes to a chemical transmission between the two neurons, neurotransmitters, right? Is it called, right? And this can be influenced by chemicals, and this chemical process can be easier when the synapses is smaller. The distance between two cells grows smaller. That is part of the learning of in natural brains, and this could also be implemented here, right? But most brain activations, unfortunately, they don't use any learning. But we can find the differences between short-term and long-term memory that we've talked about before. We can also see here. Long-term memory is what we know about the relation between documents and terms, weights that we calculated, and we simply inject this into the network. Long-term, this can change, but doesn't really. Could change. And what we think of right now, what a user is currently interested, is the short-term memory. That's what basically the document is interested now, right? What it's activated for, what it's the pattern that it displays. More or less answered the question? Further questions? Comments or anything? Not the case? So here I tried to visualize the process, and here we see that step by step more things get bold line and get more activated. Of course, there are also a lot of issues and interesting things. We have to think of when does activation end. After 2, 3, 4, 5 steps, right? We have to define something. At one point it stops, and then the most activated documents are presented to the user. Something else that comes quite natural. We can have a different. We can have in-layer connections. For example, between synonyms. In this case, we only have connections between documents and terms. But if we know that this term network has something to do with TCP/IP or server client, then we can inject this knowledge into the network by simply creating a connection there. And then activation is transmitted automatically within the layer from network to other related terms. Here we see we can use a thesaurus, for example, to add in-layer connections to the network here. We can add different layers, like an author layer, institution layer, things like that. Or we could also have hidden layers where the units don't mean anything really, where they don't have an interpretation, which is one of the strengths, of course, of the neural network algorithms. And as I've said, there are several intuitive expansions of the model. We don't have to really learn what relevance feedback is. It happens in the network. Or we don't have to learn what. We can have different query types, documents and terms, or even authors once we have these terms. So we have a quite flexible model that allows different ways to do retrieval. So a very intuitive IR model, term expansion is inherent. An inherent feature, also term expansion, something that we have not talked about yet, I think, right? Term expansion, not really yet. That's the first thing that you mentioned. Once TCP/IP is activated, at the second step, third step, network will be activated. So network and TCP/IP are now activated nodes, which represent my interest, right? And that means I have a term being activated that helps me in the retrieval that I didn't have to write down in the query. I didn't have to type. And that is called term expansion. Often users are lazy to type a lot of terms. The more terms you type, the more the computer knows about your interest and the better the results will be. And since users often don't type as many, systems have as many terms as would be nice. Systems often expand queries by adding additional terms and saying, probably is interested in network also if you look searches for TCP/IP. And this term expansion is also something that comes quite natural in the spreading activation network model. It has been evaluated in empirical analysis by Qua in the PIRC system in the track campaign and showed quite nice results, but these systems had a lot of limitations. Basically, since the term document matrix corresponds fully to the connection matrix, so we said we take the weights and inject them into our connection matrix, we basically have another realization, a different technical realization of a vector space model. Basically, we have the same thing. And something like learning, as you have pointed out, is hardly possible, difficult to implement. We have supervised in real other neural network algorithms. We have supervised learning, unsupervised learning. Perhaps through something that is used often is strengthened, is unsupervised. Supervised learning is done with feedback, saying, you have activated, we've given you this pattern and you have activated, come out with this pattern, that's okay or that's not so good. And then the weights can be changed based on this input to better find a correct output the next time. That is what supervised learning is all about. In successful systems like the PIRC system of Qua do not exploit this flexibility, neither learning nor the flexibility that we have talked about. They typically use only one or mostly two activation steps. Then they're quite good, but then we can say they're nothing else than a vector space model. But the network, of course, itself, the system itself is quite interesting, and we have, at least for once, talked about learning. Maybe we come to one of the later classes again to text mining and supervised learning, so we get a coarse idea of that things as well. Anyway, this closes our discussion on models. Any questions about the language model still or the network model? No? Seems to be easier. There are not so many numbers, right? Only very few things to calculate. Whereas the network model is, we have only discussed in a non-algorithmic way. Anyway, overview, ranking systems or models. The discussion about models has to some extent lost its importance that it used to have in information retrieval. People were very passionate talking about models and best models. And we have seen that there is a lot of equivalence between models. Vector space, probability-based model is not so different. Again, network or the spreading activation systems are not so different if we look carefully. And nowadays, more or less everybody agrees that progress cannot really be reached by inventing new models. Cannot expect it by that as well. One of the last inventions was the language models, but they were very successful, but they sometimes leave comparable performance as the BM25 weighting model that we've talked about. But what is more important is really the implementation details. We've seen that there are so many parameters in our system that we can change, and these are quite important. And for the user, in addition to the algorithm, to the effectiveness of the algorithm, there are a lot of other things that are important for him. What are heuristics? What is the user interaction, user orientation of the retrieval system? There are other things here as well. Especially in TRAC, something that we'll talk about when it comes to evaluation. The TRAC is the Text Retrieval Conference, where we can see that no real progress has been made by just coming up with a new model. Some are equivalent anyway, and we have to learn more about this in the evaluation optimization course. Anyway, homework. Now we can see if there are really no question about the language model, because there is a small homework on calculating weights using the language model. There are 2 documents and 2 terms. And one, we know about that house appears in document 1 4 times, and Zeughaus appears once in document 2. And we only have to calculate these 2 weights. And you use the linear interpolation method with a lambda mixture method, the mixture model, remember, with the 2 factors controlled by the lambda. Here is the value for lambda. And now, of course, we want to have some realistic reference collection. We use the Wortschatz-Leipzig, where you can look up the 2 words. And you can already make some guesses of what is more frequent. Maybe house or maybe Zeughaus. You will find out. Read the frequency there. Round it, of course. We assume that the collection size is 1 million. And we assume that we have a document length. You can find the V, the vocabulary size, also under Wortschatz-Leipzig. Also can be rounded very generously, right? We have to use only one number there. And probably here is the result that can help you to control